Hi guys, this is AS Chemistry, Organic Chemistry, and we are doing carboxylic acids and esters. Question 1. This question is about molecules with the molecular formula C4H8O2. Give the structural formula of the pair of chain isomers with the formula C4H8O2 that are carboxylic acids. So we start off with the simplest structure, that is a straight chain carboxylic acid. So this would be COOH followed by a CH2 group, followed by another CH2 group, followed by a CH3 group. So this is butanoic acid. Now, in order to make a chain isomer, we should introduce branching. So if we take out one of the CH2 groups and attach it to the other CH2 group, so one of the hydrogens from the CH2 will be added to the substituted CH2, making it CH3. So the structure of the new acid would be CH3, CH, we attach a CH3 here, and then a COOH. So it has the same molecular formula, but now we have introduced branching. So the name of this carboxylic acid would be 2-methyl, and the parent compound has 3 carbon atoms, so propanoic acid. Give the structural formula of a pair of positional isomers with the formula C4H8O2 that are esters. So we can change the number of carbon atoms present in the alcohol part of the ester and the acidic part of the ester. So we start off with the C double bond O single bond O ester group, and we include one CH3 group in the alcohol portion of the ester. So we are left with two CH3, two carbon atoms actually. So a CH2 and a CH3 added to the carboxylic side of the ester. And the name of this ester is methyl, and the carboxylic portion has 3 carbon atoms, so propanoate. In its positional isomer, we will switch the position of the ester group so that there are more carbon atoms on the alcohol side and lesser than 3 carbon atoms on the carboxylic acid portion. So C double bond O single bond O stays here. We have a CH2 and a CH3 group added to the alcohol portion of the ester, which leaves us with a CH3 group added to the acidic portion. And the name of this ester is ethyl, and there are 2 carbon atoms on the carboxylic side, so ethanoate. And these two esters are positional isomers of one another. Give the reagents and conditions needed to produce one of your esters in one. So reagents and conditions. So if we go with methyl propanoate, we would need methanol. Then we would need propanoic acid. Then we would need H2SO4 as catalyst, and we would heat under reflux to obtain methyl propanoate. Question 2. Calcium lactate is used in some medicines. It forms when lactic acid, which is 2-hydroxypropanoic acid, reacts with calcium carbonate. Identify the two other products of the reaction of lactic acid with calcium carbonate. So if we have calcium lactate forming, that is the uh, organic portion of the products. So the other would be, since it's a carbonate, we would have carbon dioxide and water being produced during this reaction. Two possible methods of making lactic acid are shown. So we start off with an aldehyde, which is converted into a cyanohydrin, which is hydrolyzed to the lactic acid, hydroxycarboxylic acid. The other route is we start off with primary and a secondary alcohol, which is oxidized to a ketone and a carboxylic acid, and then the ketone is reduced to the OH group, and we have lactic acid. State suitable reagents and conditions for reactions 1 and 3. So reaction 1 is nucleophilic addition. So we need HCN, we need NaCN, and we need HCl to provide acidic conditions. So these are the reagents and conditions needed for reaction 1. And for reaction 3, we have oxidation taking place. So we need acidified K2Cr2O7 and plus heat that would oxidize the secondary alcohol into a ketone and the primary alcohol into a carboxylic acid. Name the type of reaction that occurs in reaction 2. So this is the conversion of a nitrile into a carboxylic group. So this is known as acid hydrolysis. Reaction 4 uses NaBH4. Identify the role of NaBH4 in this reaction. So it converts a ketone into a secondary alcohol. So NaBH4 is being used as a reducing agent. Lactic acid has a chiral center. State what is meant by the term chiral center. A carbon atom forming four single bonds with four different atoms or group of atoms. Question 3. Many naturally occurring esters are used as flavorings in food. The structure of ester V is shown, and the name of this ester is asked, name V. So in the alcohol portion, we've got one, two, three carbon atoms. So this is propyl. And on the acidic side, we've got two carbon atoms. So propyl ethanoate. One, two, three, mix it propyl, and one and two mix it ethanoate. V reacts with a reagent to form a salt of a carboxylic acid and an alcohol. Identify reagents that could be used in this reaction. So this is NaOH aqueous, and we heat it with NaOH aqueous so that the ester hydrolyzes. Draw the distillate formula of the alcohol made during this reaction. So propyl ethanoate will result in the formation of propane 1-ol. So propane 1-ol has three carbon atoms, one OH group, and all the other positions are occupied by hydrogen atoms. So this is the distillate formula of propane 1-ol. State one other possible use of V apart from as food flavorings, so as components of perfume, or it can also be used as solvent or a solvent, a single compound. Ester W is made up of 54.5% carbon, 9.1% hydrogen, and 36.4% oxygen. Calculate the empirical formula of W. So we have carbon, hydrogen, and oxygen present. So, in order to calculate the empirical formula, first we write down their percentages, which is 54.5, 9.1, and 36.4, and then we divide these percentages by their AR values, which is 12, 1, and 16. This gives us a value of 4.54 for carbon, 9.1 for hydrogen, and 2.275 for oxygen. The next step is to divide these values by the smallest number out of all three, which is 2.275. So when we divide 4.5 by 2.275, 9.1 by 2.275, and 2.275 by 2.275, we have a carbon is to hydrogen is to oxygen ratio of 2 is to 4 is to 1, which leaves us with an empirical formula of C2H4O. State what additional information is required to determine the molecular formula of W. We would need the molecular mass along with the empirical formula to obtain the molecular formula of W. Compounds X, Y, and Z are shown. They all have the same molecular formula. Reduce the molecular formula of X, Y, and Z. So we pick any one of these and look at the number of carbon, hydrogen, and oxygen atoms present. So in the case of Y, this would be a carbon atom, this would be a CH2 group, and this would be a CH3 group. So totaling the number of carbons gives us 3 carbon atoms. Hydrogen is 3 plus 2 plus 1, 6. And there are 2 oxygen atoms present. And since all of them have the same molecular formula, so the molecular formula of each of them is C3H6O2. In 3 separate experiments, sodium is added to separate samples of X, Y, and Z. Complete the table to show the observation for each of these 3 experiments. Ignore any temperature changes which may occur. So sodium plus X. X contains an aldehyde group and an ether group, none of which would react with sodium. So there would be no visible change observed for sodium plus X. So no visible change observed. Y is a carboxylic acid. When sodium is added to a carboxylic acid, we would see effervescence and a colorless gas evolves. This would be hydrogen gas that is being given off. Carboxylic acid plus metal would form sodium carboxylate, giving off hydrogen gas. And sodium plus Z. Z is an ester. Esters also do not react with sodium metal, so we will have no visible change observed. Sodium carbonate solution reacts with methanoic acid. Write the equation for this reaction. So methanoic acid is HCOOH and sodium carbonate would be Na2CO3. So according to the molar ratio, we would need 2 moles of HCOOH. This would give us 2 moles of HCOO minus Na plus. It would give us 1 mole of CO2 and it would give us 1 mole of H2O. So this is the equation for the reaction of methanoic acid with sodium carbonate. Question 4. Many naturally occurring organic compounds contain oxygen. Such compounds may contain alcohol, aldehyde, carboxylic acid, ester, or ketone functional groups. These functional groups may be identified by their reactions with specific reagents. Compound F is a white solid which has the molecular formula C3H6O3. Compound F is soluble in water. Addition of NaHCO3 to this solution produces a colorless gas G, which turns lime water milky. What is the identity of gas G? So it is carbon dioxide, because carbon dioxide is turning lime water milky. What functional group does this test show to be present in F? So if carbon dioxide is released on addition of bicarbonate, that means the carboxylic acid group is present. When F is heated with concentrated sulfuric acid, a colorless liquid H is produced. When cold dilute acidified KMnO4 is shaken with H, the solution becomes colorless. What type of reaction occurs when H is formed from F? So when H is formed from F, we have removal of a water molecule, because of which there is introduction of a double bond as shown by the reaction with cold dilute acidified KMnO4. So removal of water molecule can either be called elimination or it can be called dehydration. Use your answers to A2 and B1 to deduce the structural formula of the colorless liquid H. So we have a molecule formula of C3H6O3. We know that it is a carboxylic acid. We know that it has a carbon-carbon double bond present, because when F was converted to H, we had a positive result with cold dilute acidified KMnO4. So we can start off with the carboxylic group COOH, and then we have, oh, but C3H6O3 is the molecular formula of F, not H. So we have loss of one hydrogen, actually loss of two hydrogen and one oxygen. So if we minus H2O from this, the molecular formula of H becomes C3H4O2. So if we have three carbon atoms and we have a double bond present, so that double bond will be present on these two carbon atoms. And now we are left with three hydrogens to place. So one hydrogen will come here and two hydrogens will come here, completing the formula of the compound H. So we've got a carboxylic group and we've got a double bond present in the same compound. Compound F reacts with sodium. Calculate the volume of hydrogen measured at room temperature and pressure, which will be produced when 0.6 grams of F reacts with an excess of sodium. So the first thing we'll do is calculate the MR of C3H6O3. So that would be 48. 48 plus 6 would give us 54. 54 plus 36 would give us an MR value of 90. So in order to calculate the moles, we have mass upon MR. So 0.6 upon 90 gives us a mole value of 6.67 into 10 to the power of minus 3 moles. So now we have moles of F that reacts with an excess of Na. So now to find out the moles of hydrogen that is liberated. So we've got one COOH group which would react producing half a mole of hydrogen, and we have one OH group which would react producing half a mole of hydrogen. When we add these two together, we end up with 1 mole of hydrogen gas being produced per mole of F. So if we have 6.67 10 to the power of minus 3 moles of F, then the moles of hydrogen would also be equal to 6.67 into 10 to the power of minus 3 moles. So we need to calculate the volume. And in order to calculate the volume, we know that 1 mole of any gas at RTP occupies a volume of 24 dm cube or 24,000 cm cube. So we have 6.67 into 10 to the power of minus 3 moles present. So these would produce a volume of 6.67 into 10 to the power of minus 3 multiplied by 24,000, giving us a value of 160 cm cube of H2 gas at RTP. So in this way, we have calculated the moles of hydrogen gas that would be present in the given sample of F, and using those moles, we have calculated the volume of hydrogen gas produced. There are two structural isomers of F that give the reactions described in A and B. Suggest two structural formula for these isomers. So we have uh, C3H6O3. We have a carboxylic group and an alcohol group present. So this alcohol group may be present on the second carbon atom or on the third carbon atom. So the structural formula would be COOH. We would have CHOH and CH3, or we could have COOH, CH2, CH2OH. These are the two possible isomers having the same molecular formula as F. Isomers J and K can both be oxidized. What will be produced when each of isomers J and K is heated under reflex with acidified K2 Cr2O7? So when J is heated with acidified K2Cr2O7 under reflux, we end up with the OH group turning into a ketone group. So CH3, C double bond O, single bond C double OH in the case of J. And in the case of K, since it's a primary alcohol, it will convert into a carboxylic acid. So H double O C, CH2 and C double OH. This is the product upon oxidation of K. Question 5. A student reacted together an alcohol and a carboxylic acid under appropriate conditions to produce an ester, a sweet smelling organic liquid Q with the empirical formula C2H4O was produced. The MR of Q was found by experiment to be 87.5. What is the molecular formula of Q? So if we have the empirical formula C2H4O, its mass is 24 plus 4 plus 16. This is 44. So we have 87.5. So 87.5 divided by 44 is almost equal to 2. So when we multiply C2H4O by 2, we end up with a molecular formula of C4H8O2. A sample of Q was hydrolyzed by heating with aqueous sulfuric acid. The resulting mixture was heated under reflux with acidified potassium dichromate to give a single organic product R. The product R was collected and subjected to the following tests. A sample of R gave no reaction with Tollens reagent, so aldehyde is absent. A second sample of R gave no reaction with 2,4-dinitrophenyl hydrazine, so a carbonyl group is absent. And a third sample of R gave an effervescence with sodium carbonate. So RCOOH group is present. What does the result of the test with tolerance reagent show about R aldehyde group is not present? What does the result with the test with 2,4-dinitrophenyl hydrazine reagent show about R no carbonyl group present? What functional group does the result of the test with sodium carbonate show to be present in R carboxylic acid? What is the identity of the single organic compound R? So, single organic compound R would be uh, it's a carboxylic acid C2H4O. C2H4O. So one of the groups would be COOH because it was hydrolyzed by heating with sulfuric acid, and C2. So we have got C2H4, C2, C is left, and H4H3, CH3, COOH. So it's ethanoic acid. Question 6. The first stage of cheese making is to produce 2-hydroxypropanoic acid, lactic acid from milk. Other than the use of a pH indicator, what reagent could be used to confirm the presence of some lactic acid in a sample of heptane 2-on? State what observations you would make. So we could add sodium carbonate, and the observation would be effervescence and a colorless gas evolves, which turns lime water milky, because this would be carbon dioxide gas evolving. We can also add sodium metal, and we would have a evolution of hydrogen gas. We can have, since it is an it is a carboxylic acid, we can form ester, but then heating would be required. And since that carboxylic acid contains the OH group that can be oxidized, so we can use acidified K2Cr2O7, and the solution will turn from orange to green. So there are a lot of reagents and observations that can be used as a test for the presence of lactic acid.